Hi, today we're going to be starting chapter 4, which is all about the applications of derivatives. So now we've gotten pretty good at being able to find derivatives. Now we've got to start applying that knowledge somewhere. So we'll start off with 4.1, extreme values of functions. So we'll be talking about what an absolute or global extreme value is and how to find them. We'll be talking about local extreme values and just finding all the extreme values that we need to find. So if we look at this function f of x on this domain, the domain's about from 0 to 2.7. And we wanted to explain, okay, what are the important values about this graph? We'd probably talk about, okay, we have a minimum value down here. Well, that's a really fat mark there. We have a really important value up there, so that's the minimum. Let's see if I can fix this pen. And this would be the maximum up there. Okay, because on this domain, that is the very smallest this gets, that would actually, instead of just calling it the minimum, that would be the extreme minimum or the global minimum, and that would be the extreme maximum or global maximum. But we also have these 2 points, these 2 critical points here, one there and one there. These would be called local maximums and local minimums. So this one right here is a local max. Okay, if you were just looking at the graph here, if we broke it down to just a picture of that, well, you'd say the maximum of that graph would be right there. So there is a local maximum there. And this point is the local minimum. To where if I looked at a window like this and said what is the minimum value of this function, you'd probably say that point right there. Okay, so we're going to look at different ways we can find these. Now notice that our local mins and local maxes, all right, what is the slope right there at the tangent, the slope of the tangent line there and the slope of the tangent line there? Hopefully you notice those slopes are 0. So whenever we're trying to find a local maximum or minimum, we just take the derivative and set it equal to 0. That will give us the slope of 0, and it should tell us, then we can plug that value in and find out what is our local maximum and what is our local minimum. Now, lots of AP questions get very, very particular between saying what is the local minimum and where is the local minimum. So what is actually talking about the y value or the value of f at that x point. Where is the local minimum is actually saying what is the x value. So just as a heads up, when we start practicing some of our AP problems and start practicing some of the multiple choice questions, you need to be really careful and read those questions carefully of, is it asking you for where is the local minimum or maximum, or what is the local minimum or maximum? So we need to define a few things first. So the absolute extreme values, also known as the global maxes and global mins. So it's defined here as the absolute maximum on D is where it's greater than all the other values, basically, is what that says. The minimum, it would be where it's smaller than all the other values, so that makes perfectly good sense. The extreme value theorem says for any function f, so any function f, doesn't matter what it looks like. Oh, that's not a function anymore, sorry. Let me see if I can erase this part. Let's just say that was our function there. Pretend like the graph was angled like this so that it is a function. So here's our graph, and we're growing from like negative, I don't know, we'll just call it, instead of a negative, we'll just call it from A up to C here, or no, they're calling it B. So from A to B, there is a maximum value and a minimum value on this interval. So if we were looking at this, yep, looks like, oh, that's probably the maximum value and that's probably the minimum value. But it doesn't matter. As long as f is continuous on an interval, there will always be a maximum and minimum somewhere on there. Now sometimes you'll have the minimum will be repeated twice. It'll be the same value, or the maximum. If that is, instead of saying the minimums, that's not really a word, minima, if it is, so you just change that to an A. Minima, if there's two minimum values that are the same thing, you call it minima. So just a little vocab there for you. So pretty simple and basic, extreme value theorem just says on a closed interval, if f is continuous, you have a maximum and a minimum. Local extreme values are a little bit different. Okay, on some interval, a local minimum value is at c if and only if f of x is less than, for a maximum, f of x is less than f of c for all x's in that interval. Okay, same thing for minimum, is just f of x is always greater than all the other values compared to f of c on that same interval. Okay, this is a big side note. A function f has a local maximum or local minimum at an endpoint c. So your endpoints are considered local minimums or local maximums. So just wanted to put that out there for you. So local extreme values are defined if a function f has a local extreme or a local maximum value or a local minimum value at an interior point, and the derivative of f exists at c, then the derivative of f at c is equal to 0. We showed that in the graph before. That's how we find those local minimums and local maximums. So whenever we're asked to find those, we'll just take the derivative, set it equal to 0, and solve. Okay? We just have to watch, are they asking for where, or are they asking for what is the value? A critical point is a point in the interior of a domain of a function at which f prime, or the derivative of f, is equal to 0, or the derivative of f does not exist there. So critical points are either a local min or max, or where the derivative does not exist. So those are also critical points. Okay, that'll be when you have a function that's broken into two separate functions. If the derivative doesn't exist, that's still a critical point there. For example, if we had this function that looked like this, okay, with a closed circle or maybe an open circle there, and then we jumped to this function like that, there is no derivative there, but at this value we'd call it maybe, at this value we'll call it maybe c. F of c is a critical point because there is the derivative does not exist there. Okay, I want you to hit pause and just identify each x value and label it. Is this a local minimum, local maximum, global minimum, global maximum? So just label this graph. Go. Okay, hopefully you labeled f of a to be a local, it's not a global, but a local minimum. Okay, that endpoint there, that is a local minimum. All right, then f of c, okay, that, remember we said that has a slope of 0 there, so it's a local max. Well, It also, on the domain from A to B, there's no other value that is higher than it, so it's not just a local max, it is actually the global maximum for this function because it's just going from A to B. There's no other point that's higher than it. Okay, and then finally f of B, right, that point down there is, there's no other point lower than it. Okay, so it is the global minimum. Okay, so that's how we would label this graph. The extreme value theorem says on any interval where we have a continuous function that there will be a global max and a global min. So from f of A to f of B, we do have a global max and a global min. So that just confirms the extreme value theorem. Next, find the extreme values using analytical methods. In other words, you'd have to test the endpoints. So test -1 and test 1. And you need to take the derivative and set it equal to 0. Right? Find out where would the extreme values here be. So hit pause, give this a shot, see how you do. Okay, so first I'm just going to find g prime of x. And I know that the derivative of e is e to the x, but I've got a negative x up there, so it's going to be, the derivative will be negative e to the negative x. Okay, so I want to find out when is this equal to 0. I know that any exponential equation like this never hits 0. It'll approach 0, but it'll never quite get to 0. So I don't have the ability to say there's a local minimum or local maximum here because I can't ever find when this is equal to 0. It never is. Definitely not on the interval from -1 to 1. But I do need to, oh, by the way, if you were to graph this graph, it would look something like, it would kind of come up like this and approach 0, but never quite get to 0. So that's kind of what that would look like. Anyway, we need to start plugging in. Okay, what is g of -1? Well, this is the function, this was g prime that I graphed, g prime of x. So g of x would just be, the same sort of thing, just sloped that way. So if I said that this was at -1 and this is at 1, we know that this point here on our interval really is going to get rid of this part of the graph, and then I can pretty much get rid of that part of the graph. So I know I'm going to be just looking at g of -1 is the maximum value. So let's plug it in. E to the -1 just becomes e to the first, which is e. So that would be my, so at x equals -1, my global max is e. Okay, so this says find the extreme values. The extreme value is e. If it was saying where are the extreme values, you'd say the extreme value is at -1, or the global maximum is at -1. Okay, we need to give the value here too, so it's e. Then we know the other one, g of 1 is e to the -1st. Okay, so that would just be 1 over e. So 1 over e is the global min, so this is global minimum. Alright, so if the question asks where is it, you'd have to say it's at 1, but the global minimum is a value of 1 over e. Next problem would be find the extreme values and where they occur. So hit pause, give this a shot, find the derivative, see what the extreme values are. Okay, so we need to find the derivative and then set it equal to 0. So the derivative y prime is equal to, use the power rule, 3x squared minus 2, and we just need to set that equal to 0. Okay, so we can start solving 3x squared equals 2 by moving that negative 2 over. Divide by 3, x squared equals 2/3. So x is equal to plus or minus square root of 2/3. So we have two values here at a value of negative root 2/3. That's one of our extreme values, and then at positive square root of 2/3. Now we know that a cubic function looks like this, so we can plug in the negative square root of 2/3, so we really want to say, I'm going to switch forms and just call this f. F of negative square root of 2/3 is equal to 5.09, and f of positive square root of 2/3 is equal to 2.91. So this first value is a local max. That would be the function up there, a local maximum. The second value, which would be down here, would be a local minimum. Okay, now thinking about the extreme value theorem, I thought it said that we'd always have a global max and global min, but that was on a closed interval. This isn't open. This goes forever to the left and forever to the right. Since we do go on forever and it's not closed, we don't have any global mins or maxes here. So just these two local points are our extreme values. That pretty much covers it for today. Please bring any questions that you have into us or into me, and we'll talk about them in class. Thank you very much.